It's our great. Oh, yeah. You don't mind being recorded, are you?
No, that's okay.
All right. So it's a great pleasure to have Tom Reichert visiting us. He's actually from Frankfurt, staying with us until middle of December. So we'll have plenty of time asking all kinds of questions about Frisco. And Tom got his PhD, as I learned, about 1.5 years ago from the University of Frankfurt, and since then he's a postdoc at the Institute of Advanced Studies in Frankfurt. Yeah. And now he is visiting us, and he will tell us everything about three-fluid model for heavy ion collisions. So please take it away.
Thank you very much for the nice introduction and for having me here in Berkeley for this 2-month collaboration. So far I haven't traveled around too much. I studied in Frankfurt, I did my PhD in Frankfurt, I do my first postdoc in Frankfurt. And mostly during my studies I have been concerned with transport models, mostly the UOQMD model, studying various observables, flow, particle production at rather low energies, but also stretching to the LHC. And this new model is something that I started developing in a 3-man team with Markus Bleicher, which most of you I think know, and Christian Spieles. He also studied in Frankfurt.
Markus was also a postdoc.
Markus was also a postdoc here. I think Christian was...
He was also here.
He was also here. Christian is now actually working in a bank and is only partially contributing every Friday once he comes to the institute. And yeah, this model that we're developing is called Frisco. We have no idea for what the abbreviation stands for. If you have any suggestions, please tell us. And it's a 3-fluid model with continuous freeze-out for intermediate energy heavy ion collisions.
So what is the logo on the top right?
That's the heavy ion T.
Ah, okay, I should know this. I embarrassed myself.
I found it on the webpage. Maybe it's not anymore the correct one. But
I think it's Xindian made it.
Yeah, right. Looks like Xindian, yes.
Yeah. Today I will give you a little bit more of an introduction because it's a new model and I want to motivate it in a little longer way. And finally, I will also show some preliminary results. All right, so what we are all interested in is to study QCD. And there are many sketches of the phase diagram all around the world. I chose to pick this one, which was shown at Seaport by Christian Fischer, which essentially has everything that we nowadays know about the phase diagram. I adopted it a little bit and put in some more points. Basically, you can separate this phase diagram into the hadronic phase and the quark-gluon plasma phase. What we know from the lattice is that there's a crossover transition at 0 chemical potential, stretching out to mu over T equal to some number, 2, 3, around that region. Then you see in the back, there are the chemical freeze-out points. These are these light purplish points, which arise from thermal fits to measure particle yields. And apparently they are very close to the chemical, to the phase transition here at these high energies, which led to the conclusion that maybe everything is super thermalized at these energies. What I've put in here by hand is a calculation we did using UOQMD a couple of years ago, also calculating the chemical freeze-out, and what we saw is that we also get the chemical freeze-out points without phase transition, so there's some ambiguity going on there. And then there are all the most recent predictions for the critical endpoint coming from critical scaling, from novel lattice extrapolations, from holographic. A recent one from Claudia Ratti, which just appeared a couple of days ago. And yeah, so there's many things going on in this energy regime. And most of the people now are quite sure that if the critical point exists, it should be located around this region. And this region is further interesting because that's the region that FAIR will probe once it is finally built and running. And also the star-fixed target program will scan this region. Unfortunately, where temperature and chemical potential are thermal properties, unfortunately, we don't have QCD in a box in an experimental setup. We only have heavy ion collisions and also neutron stars, which are non-equilibrium processes, and they are very dynamical. That's a sketch you see down here. So in order to map something from these experiments to the phase diagram, one has to rely on some kind of dynamical model, which mostly are transport models in all its variety, or hydrodynamic models. And another motivation typically is the connection of heavy ion collisions, which you see down here, to a neutron star to binary neutron star mergers, which have similar temperatures and densities. However, in my opinion, the most similar thing here is actually the color scheme that was chosen. But yeah, that's personal. Yes.
So when you get your phrase up, what is your criteria?
In your QMD?
Yeah.
What we did back then is, so the kinetic freeze-out is easy. That's just the last collision. You have that in a model. For the chemical freeze-out, and here we only did pions, we said that basically when a pion hits a nucleon, it creates a delta most of the time. The delta decays back to a pion and a proton. And in your QMD, we have the whole time evolution of the system, the whole collision history. And what we can do is go back through all these pseudo-elastic collisions, pion-proton doing a delta, delta decaying back to pion-proton, until we find the first reaction that created the pion without having a pion before. And then we say this is roughly correlated to the chemical freeze-out. Then we coarse-grain the whole thing, run the coordinates through that, and then we get these freeze-out points, which are, well, matching with the chemical freeze-out points quite good. In theory, or at least from a modeling perspective, you can dissect the phase diagram into two regions. At the very high energies, where we are sure that we have quark-gluon plasma, usually we model it in the following way. We have an early initial super Lorentz contracted nuclei with gamma factors up to 1 or 2000. We have a very early non-equilibrium phase, which you see modeled here. We then create a quark-gluon plasma, which usually in theory is modeled by hydrodynamics, because there you can just plug in the equation of state that you get from the lattice. Later on, you do Cooper-Frye, turn the fluids again into particles. You let them rescatter via some afterburner, your QMD, smash, whatever you want to choose. And finally, you freeze out. And with this procedure, you will learn something about the quark-gluon plasma and everything that's going on. This is more applicable to the higher energies. If you go to lower energies, simulation is working, that's cool. That's a simulation at 1.23 AGeV, so the hardest energy. This in the phase diagram is down here. That's not even on the phase diagram. Everything is super slow. The Lorentz contractions on this order of magnitude of 1, maybe going up to 4, so the nuclei are not really Lorentz contracted. Everything is out of equilibrium. It takes a long time until the system really has fully compressed and created the fireball. The viscous corrections are quite large. Spectators do decouple on a similar time scale as the whole reaction and not directly as at high energies. And this is why usually in this energy regime, one does not use hydrodynamics, but more relies on transport models. Now, you already see that these critical endpoint predictions are in this energy regime and not where we use hydrodynamics, because in hydrodynamics, that would be cool. You just plug in the equation of state. You describe your quark-gluon plasma and the phase transition. There you can do that easily. In a transport regime, you cannot do that because we still haven't understood the deconfinement transition. We have no idea how to model that in a transport model. So this is kind of summarized on the slide here. Of course, there's much more pros and cons, which I could have listed, but I just wanted to focus on the basic stuff. So hydrodynamics is solving the hydrodynamic conservation equation. Pro of hydrodynamics is you can model a quark-gluon plasma in a phase transition. Everything is integrated out into the equation of state. However, you need local equilibrium, which at low energies takes time to build up. And the fireball is only created at rather late times. In transport, you kind of solve some kind of time-dependent and particle phase-space distribution, either in a BOU or QMD way or other ways. The pro here is you can treat non-equilibrium processes. The contra is you cannot model the quark-gluon plasma. And that's where we want to jump in and combine the pros of both of these, which is especially focused for this energy regime. So what we want to do is, or are already doing, is develop a 3-fluid model with continuous freeze-out. 3-fluid, or first of all, hydrodynamics for the simple reason we can plug in a quark-gluon plasma equation of state and describe the phase transition. 3 fluids, which we separate into the projectile, target, and the fireball for a specific reason. With that, the fireball can be built up over time. If we first only describe the projectile and the target as a fluid, we propagate them, we can calculate some kind of friction in the overlapping region, and this will build up the fireball over time. As said, all the matter properties are in the equation of state. And usually, a second caveat that hydrodynamics has, or in general, the hydrodynamic setup that is used at high energies, which is an early transport model, an intermediate hydrodynamic model, and then an afterburner. Here, everything is in one model. You don't need afterburners, no hybrids anymore. Everything is in one model. And over the typical Cooper-Frye prescription, we also improved that with continuous decoupling mechanism. And Cooper-Frye, although being good in itself, you always need to put in some criterion which tells you, now you go from hydrodynamics to particles. And this, although is sophisticated, is always just put in by hand. It also has other caveats, like usually you don't subtract the momenta that are frozen out, so there's no feedback to the hydrodynamics. So this has, although being good, has a lot of caveats. And when we do continuous decoupling, actually the local scattering rate determines which amount of the particles actually freezes out. Questions so far?
But the fireball has to hadronize or freeze out, right?
Again?
So we say there's no need for no more hybrid or afterburner.
Yeah.
But the fireball itself has to all these freeze out.
With a continuous decoupling. I'll come to that. I will show you the technical details on the next slides. Short history, we are not the first people considering that. In the past, well, 40 years, there have been a lot of hydrodynamic models using 1 fluid, 2 fluids, and 3 fluids. None of them is using a continuous freeze-out prescription. All of them were using Cooper-Frye. The most recent one published last year is the muffin model, which is very sophisticated and more restricted to higher energies because of some technical details in the friction. And then there has also already been a continuous freeze-out model with a single fluid. This is the hydrokinetic model published, well, 15 years ago. And this is an extract that you see from a study using this HKM model, where you see a comparison of what is this pion spectra done with Cooper-Frye. Those are the dashed lines at 75 MeV and 160. And then you see that the continuous decoupling gives a different slope for these pion spectra. So there's a qualitative difference when doing that. However, in that model, they never showed everything that they can do with the model. They only usually just show some spectra. They don't show the time evolution, showing that everything is conserved. And this is something we want to improve on and also merge it with a 3-fluid setup. All right, so technical derivation, although the model itself, most of it is mostly phenomenological. Basically, you start with relativistic hydrodynamics for energy and momentum and the conserved charges that you want to consider. You then split the energy momentum tensor into the projectile, target, and fireball. So far, everything is still valid. And then you say, I make 3 equations out of that. So T mu projectile equals 0, target, and fireball. And on the right-hand side, you then don't write 0, but you write some friction terms. So then you end up with an equation like this. So you say that the derivative of the energy momentum tensor is some kind of friction plus a unification term plus a decoupling term. And by construction, the sum of all of these friction terms must add up to 0 to fulfill the equation that you started with.
What is FL down there? This is for all the 3 different components?
That's the fluids.
So this is gold. So I have 3 equations, one for projectile and target.
You have this equation for the projectile, for the target, and for the fireball.
And where are the projectile and the fireball coupled? Where do I see? I mean, they must be coupled because you move energy from the projectile and the fireball.
Yep.
Where is that being done?
This will come on the next slides, but basically the friction brings energy and momentum to the fireball. Unification then brings in the baryon number to the fireball, and decoupling is then the freeze out from the fireball to the detector. Okay. It will come on the next slides.
What do you mean by coupling add to 0?
Well, you have to conserve this equation for the whole system. If you artificially split the T mu nu into the projectile, target, and fireball, the sum over these and then d mu nu must remain 0. And if you then say, well, d mu nu, T mu nu projectile is this friction, the friction sum over the projectile, target, and fireball must add to 0 to fulfill this.
So coupling, what do you mean by coupling?
By coupling, I mean, for example, the friction term. But when two cells of the projectile and target are overlapping at the same spatial location, we put in a friction term, comes on the next slides, and this determines how much we subtract from a projectile and target and put in a fireball fluid.
Okay. So, yeah, each of them adds to 0 or total adds to 0.
The total.
Okay.
There are some correlations because when you run with a symmetric projectile and target system, of course, the sum of projectile and target must equal the friction of the fireball, but in general, only the total sum must be 0. Okay. All right, so this is Frisco in a nutshell. I will dissect this further on the next slides. So basically, we have ideal hydrodynamics on the left-hand side. Then we have on the right-hand side friction, which brings energy momentum into the fireball. We have unification, which brings in the baryon number and the remaining energy and momentum that is left in the projectile and target. And we have continuous decoupling, which is based on the local scattering rate and the expansion rate of the system. And in this setup, by enforcing that all these terms add up to 0, we have exact energy conservation, momentum conservation, and conservation of charges over the whole system.
By ideal hydrodynamics, you don't have viscosities.
No, we don't have viscosities. Qualitatively, we introduce viscosity by the friction term, but within a single fluid, we only do ideal hydrodynamics. So let's start on the left-hand side with the propagation part. Well, first of all, we have to initialize our projectile and target. For this, we have a Saxon distribution with typical parameters. And here we have modeled two variations. One is for debugging, which is called the ensemble averaged simulation, where we just put the straight density distribution onto the grid and say, this is our projectile and the target. And we have a second mode, which can be used for event-by-event simulations, where we sample nucleons based on this distribution. And by putting Lorentz-contracted 3D Gaussians for each of these nucleons on a grid, we can kind of get initial state fluctuations. But this is still in the Kinderschuhs, and at the time we are just considering the ensemble averaged initial state. To solve the hydrodynamics, we are using the sharp and smooth transport algorithm, well known in our community. So basically, under the assumption of an ideal fluid for the energy momentum tensor and the charge currents, one can derive the equations of motions for the energy current, the momentum current, and the charge current. This is then solved by the Shasta on a Cartesian grid. And well, yeah, then you get the propagation of your fluids. This is solved, as mentioned previously, for the projectile, target, and fireball separately, and the friction is then put onto the system at the end of each time step. To close the equations that you have here, you need an equation of state. And here we assume for the projectile and target a pure nucleon gas, and for the fireball at the moment a hadron resonance gas, because that's the most well understood before going into the direction of putting in phase transitions and stuff like that. The HRG that we're using is in line with the one that is used in UQMD version 3.4, because that's what we have in hand in Frankfurt. This also coincides with the particle data group, not the most recent one, but the one from, I don't know, 2 or 3 years ago. So those are the particles that are in the model. The equation of state is tabulated in a linear table from 0 to 200 MeV in temperature, and in density, in real density, not divided by ground state, from 0.005 to 6 inverse Fermi cubed. However, we have seen that extrapolating from 0.005 to the vacuum on a linear scale actually introduces a huge error in our simulation. One can get confused of that, but the point is when we do the continuous freeze out, also these cells at the edge of the system, which have a very low density, contribute to the overall particle number. And when we want to conserve everything, a linear interpolation from here to 0 is actually not good, and the error adds up. That's why we have a second logarithmic table going from here to what we consider vacuum, 10 to the minus 12, in order to conserve everything we have on the grid. Currently, we're working on an excluded volume equation of state with 0.3 Fermi. cubed. Or I have to check if that's the radius or the volume. But this is still in the Kinderschuhs, and for debugging purposes, we are only using the ideal HRG.
What does excluded volume mean? In this context?
Excluded volume means when you derive the equation of state in a grand canonical way, you can plug in, similar to a van der Waals gas, an excluded volume, which then at the given temperature increases, sometimes actually even decreases the pressure. And overall, we have seen that this is necessary to describe the correct pion yield. And yeah.
It's a hard sphere gas.
Yeah, hard sphere gas, exactly.
You mean you trap the gas out?
Well, these formulas up there are point-like particles, and now you give them.
You give them a size.
The size.
Gotcha. That's okay. So no form factors.
Well, if you wish.
No form factors.
The mother of all form factors, right?
Yeah.
At the moment,
It's like quark, right?
yeah, it's like a quark.
Quark size. That's very quark.
At the moment, the equation of state that we have tabulated, because we need very high precision in the equation of state, is only tabulated at rho s equals 0 and net isospin density equal to 0. The strangeness density.
Okay.
Also, is the excluded volume the same for all particles versus treating pions and protons?
In this setup, it's the same for all of them. One can separate it, and there are many studies doing that. For debugging purposes and just seeing the effect, we were thinking of just give a fixed volume to all the particles. Strangeness is kind of hard to conserve because for that you actually need to calculate the equation of state along the third axis in the full-fledged mode, because in the end what you get from the model is the kaons decouple earlier, then you build up net strangeness density in the system, and so for this you have to model the equation of state really along the third axis. However, for isospin, one can use a trick. In our model, all the hadrons are degenerate in isospin, meaning we only have nucleons and not protons and neutrons. But we can separate them in a thermally motivated way by saying the nucleons are the protons and the neutrons added up. And then for each of these, we put in a factor which is typical for thermal systems. So e to the isospin times mu e over t. And by construction, if you add the protons and the neutrons here together, this will add up to 1, so the nucleon number overall is conserved. If you write that down for the whole hadron list, you end up with a polynomial determining the mu I, which is not the real mu I of the whole hadron gas, because this only allows to shift isospin within a given hadron species, so from protons to neutrons, but it doesn't allow to shift isospin from nucleons to pions. So this is not a real mu I, but it qualitatively gives the correct splitting. All right, now the interesting part, the friction term. At the moment, the friction term is modeled in a way that was already done by Michustin and his collaborators in the early 90s and of the 80s. And what they say is the friction or the energy momentum going into the fireball is modeled by the inelastic cross-section of nucleon-nucleon going to nucleon-nucleon and something else, then averaged over all momenta, multiplied by the relative velocity and the densities. And in this way, you get a friction term that builds up energy and momentum in the fireball. In practice, the sigma is modeled in a way that it separates actually the cross-section for energy transfer from a cross-section of momentum transfer. Everything written down in these old papers. And it also assumes that in a nucleon-nucleon to nucleon-nucleon X collision, everything that is flying towards the forward hemisphere, in the end, from the projectile, what is flying to the forward hemisphere is going into the fireball. Everything else stays in the projectile, and for the target, that is vice versa.
This is some kind of momentum flux or current, right?
That's right. Yeah. At the moment, with the friction term, there's no transfer of baryon number into the fireball yet. We want to improve on that because this gives a more continuous transition of the baryon number into the fluid, but this hasn't happened yet.
And I thought you have on the previous slides you had something for the baryon number conservation equation where you transport baryon number from
Yeah.
So this S fric or whatever.
Yeah.
So this is not implemented yet, this S-fric?
The S-fric is there because from a technical derivation, the term exists.
Yes.
But this is 0.
Oh.
So baryon number is only transported by S unification. This exists, but it's 0 at the moment.
Okay.
If we plug in a mechanism for that into the friction, move forward. Yeah. We would need to write down a similar equation for the S. And then we also get friction for the baryon number. At the moment, that's not implemented. Realistically, because we had the procedure to do that from the old models, that's where we started using that. When the relative momentum locally between the projectile and the target gets very small, the friction term vanishes, and then you can assume now the projectile and target locally are thermalized with each other. And then based on a relative rapidity of 2 cells, we then just say, well, you're thermalized, we just put you in the fireball because you're one system now. And this at the moment is parameterized just by a rapidity cut and relative rapidity. I have to admit, at the moment, the delta y is quite large. It's actually 1.3 units in rapidity, which is barely the whole fireball. This comes from the fact that we don't yet have a friction term from the baryon number, and having chemical potential in the fireball turned out to be important to get the pion number right. That's why this parameter still is quite large. As I said, we want to improve on that, put in a more realistic cross-section also for the baryon number transport, and then we can make this parameter smaller and bring it to the size of the average thermal rapidity.
So how do you decide when delta P gets small? Is that a parameter of your model, or does that come somehow dynamically?
That's done by this delta y. So you have the rapidity of this.
Oh, that always runs. This unification term always
runs.
Oh, okay.
Always runs.
Yeah, okay.
Once a projectile and target cell at the same place in relative rapidity.
Once they close enough, then this thing becomes
effective.
Okay.
Exactly.
And Y1 and Y2 are this is the 1 and the 2 from.
That's projectile and target.
Yeah.
Can you go back to your previous slide again? I have a question about the cross section. So you have fluid, right? But this cross section is for hadrons, is that right? How do you calculate?
That's for hadrons, yeah. This is in the end thermally. So you plug in a distribution function, which here is Fermi distribution. You thermally average that and do some integrations over half hemispheres and everything, and then you end up just with an average cross actually. And now comes the fun part, the continuous decoupling part. For that, for the form momentum that is decoupling and the baryon number that is decoupling, you can separate this into 2 parts. One is the local emissivity, and the other one is the probability of escape. So the emissivity is encoding, given a cell in the system, what is the strength of the emissivity of the cell for a given hadron species. And the other one tells you, well, now this cell is emitting particles, but they still need to propagate through the medium to reach the detector. And the probability of escape, well, gives you the probability of this particle escaping. Yeah.
So if I have now a particle which doesn't make it,
yeah,
then it gets put back where it started.
Yeah.
It doesn't not allowed to move halfway.
Yeah.
Okay.
In an ideal world, you would want to put it into the fluid.
Go for at least one mean-free path or something.
Yeah.
Like that. Yeah. Okay.
But for this, you would need to in parallel transport the hadrons and the fluids.
And that's not being.
And with the amount of test particles and cells that we have, this is unfeasible. So one assumption is when it gets absorbed, we put it back into the original cell. Okay. That's one assumption. This emissivity here is split into 2 parts. First of all, there's the density of the particle species that you want to admit at a given space-time point. And then you write this in a similar way to a relaxation time approximation, and you scale this by the relaxation time or the inverse scattering rate. For the probability of escape, you integrate from the cell where you start to infinity along the trajectory of the particle, and you integrate over the scattering rate, which in each cell in the future is the sum over the scattering rate among all of the hadron species that are there in our gas. So we can dissect this further. First of all, the F that we have here has to put into particles to propagate them. So when you're running a BOU type, where you also propagate a density, you usually do a test particle ansatz. However, in a BOU, you usually use a fixed rate of particles per test particles. And if you want to use that for thermal distribution, to get roughly 1% accuracy, you need 10 to the 6 test particles, which is quite a lot. And this is now for one species in one cell. We have roughly 1 million cells on the grid and 100 hadron species. So running this is impossible.
Maybe you want to explain, I'm not sure if everybody here is familiar with the concept of a test particle.
A test particle basically is a way to represent a distribution function. So what you see here is a thermal or Jüttner distribution function of nucleons and pions. And with test particles, you basically split this distribution up into a fixed number of test particles, which in total represent the integral over this distribution function. And usually you give each particle a fixed weight, say 1/20, 1/100, so that 100 particles together make up one real particle, and their momenta are distributed with this distribution function. If you don't know your distribution in a transport model, for example, you need to use a fixed weight. However, because we're doing hydrodynamics, we know that the local distribution function is a thermal one, and then we can use a trick, which is actually not giving each of the particles the same weight, but we give each of the particles a different weight based on the method of Gauss-Laguerre quadrature, which basically is an integration technique. But instead of summing over all of these different blocks here, you can just say, this is now a test particle at momentum, whatever, 3.8, with a given weight. In the low momentum part, you have more particles, and then everything spreads out towards higher energies. Momenta. With this method, you get a 0.1% accuracy with only 500 test particles. So this is quite fascinating. Basically tells you that Gauss-Laguerre quadrature is a good method of integrating exponentially falling off functions, but we can make use of that and say, now we have test particles with different weights. And as I said, this gives a dramatic speed up.
When you say the accuracy, is that the relative accuracy compared with doing the exact thing, or
with doing it exactly? Yeah. So you can integrate this just really numerically, very fine. And then you say, I will now take 4 test particles. You get, maybe you don't see them. There are these dotted lines which represent the test particle blocks. And if you add those up for 8⁻³ test particles, you get an accuracy of 0.1%. We do that in all of the 6 dimensions, positive px, negative px, py, and pz. And this gives them the 512 test particles.
So it's essentially Monte Carlo integration with a clever method, right?
Yeah.
That's your test particle, it's actually the Monte Carlo points in the Monte Carlo integration.
And we also want to avoid a randomness in the system, which you always introduce when you really Monte Carlo it. Right. And in this way, you have, if the number of test particles here also increases, for debugging, we use 8 in each direction. For real physics simulation, we would also pump that up. And then we have an exactest representation of the distribution function.
But the weight is computed from this.
The weight is actually no. The weight comes actually from the Gauss-Laguerre method itself.
Okay.
So
but you need to know the curve usually.
That's what I mean.
Yeah. Okay. Yeah, you know the curve that you want to integrate. Yeah.
But the curve is universal or is thermal distribution?
That's a thermal Jüttner distribution. Because we also want to do that for cells that are moving, so we have to do that for the Jüttner distribution. And basically, we split the Jüttner distribution at the peak to negative and positive directions, and then always integrate, because this goes from 0 to infinity, from the peak to infinity, and then we have to shift this to the peak and scale it a little bit. But this is how it's done in practice.
Let me ask a stupid question. If you know the curve, you should know the integral. So why do you need the test particles?
Because the test particles should appear in the final state in the spectra.
Okay.
And if you just have the integral, you don't have particles to propagate through the medium, right? If you put the whole integral into one particle, then you again introduce randomness because you need to run the whole simulation many times. And if you dissect this in very small parts, you can only run the hydrodynamics once and directly get the ensemble averaged result. So in the end, we only have to run everything once and get all the spectra. Of course, we don't get fluctuations, but
Okay, got it. All right, thank you.
so now we have the F that is going into the emissivity. We have it separated by particle species and by momenta in all three directions. Now we have to talk about this relaxation time. First of all, you can boost that into the represented by the relaxation time in a local rest frame for a boosted cell by this gamma factor here. And then locally, you have some freedom to decide what actually goes into this. So usually one would say this is kind of the inverse of the scattering rate, which is calculated in the usual way. So it's folded with the distribution function of the particle species with which you're interacting, times the cross-section, relative velocity. Of course, you conserve also momenta and energy. But if you look into studies which did something similar with pen and paper, using Kadanoff-Boehm equations, you will see that the inverse of this, if you write down a continuous decoupling scheme, is somehow correlated to the damping width that you have in Kadanoff-Boehm equations. And this motivates to also add something like the actual width of resonances. And then what we also added in, and we could motivate this together with Volker in May, based on a Boltzmann equation, we also added the expansion rate of the system, which is just the four divergence of the four velocity, which basically ensures once you reach very low densities in the end, the scattering rate drops because the temperature gets small, but you still have stuff in your fluid. And with that expansion scalar here, you are sure that this really is getting emitted from the system, because then the emissivity is not going to zero when the scattering rate is going to zero. And then for the probability of escape, we have another problem, because consider a particle that now wants to be emitted from this point in space at time t0. Now, if we propagate that through the medium at t0 plus delta t, the particle is now here, but the fireball has also increased because the whole medium is evolving. And if one more time step into the future, we have the same problem again. And for this one actually needs to have a self-consistent knowledge about the future of the system to calculate the scattering rate in the future with the densities and temperature in the future, which we don't have a priori. What we do for that is before we run our real simulation, we run a pre-calculated 3-fluid hydro simulation without freeze-out. So we just run the hydro until whatever 40, 50 Fermi without freeze-out, under the assumption that all these particles that are emitted and scatter somewhere are already included in the hydrodynamic simulation in the future if we don't freeze out. And then you can iterate this process, run the calculation with freeze out, write out the energy momenta and the temperatures and everything in the future, iterate that a couple of times, and then you get a self-consistent description of the future. We have tested this, and it turns out that actually already after one iteration, so you do pure hydro, freeze out, and then you do another freeze out, the final spectra are already changing with less than 1%. So that this is luckily converging quite quickly. Of course, in the end, when the model is done, to do a full physics simulation, we will do it 3 or 4 times just to be sure. Before I come to preliminary results, let me give you some outlook. The first thing that has to be done in the future, of course, is strangeness and isospin conservation in a full 4D equation of state. If that is done, you can also use other equations of state, extrapolated lattice, current mean field, excluded volume, MUSES, which is a collaboration from Houston. And then you can study all sorts of things with this model. For example, charm diffusion. We can directly plug in full-fledged and medium spectral functions because we have a local definition of temperature. We can calculate dileptons without using shining because we have the distribution function is represented in such a way that we can really put them in the row, and let it decay and propagate the dileptons actually really through the medium. Of course, they are not getting absorbed, but maybe once in a while they get absorbed, and we can study all sorts of things with that. We can do HBT. We can couple the hydrodynamics to, for example, a sigma field. We can do viscous hydrodynamics in the future, and of course also do cluster production, either thermally or with coalescence. And yeah, there's a bunch of bullet points because there's much more to do with that model.
But if you do viscous hydrodynamics, aren't you getting in a whole, are you opening a can of worms because you have your friction guys and you have your viscosity, and how do you make sure that you double or half count or whatever, right?
We didn't do it yet, so
it's future.
It's in the future, yeah.
The next PhD student does
Next PhD student.
No, I think you just compute that, right? Actually, at each step, you compute the viscosity from your code or from fraction.
Yeah, but he has already some kind of viscosity.
I know, that's a fraction, right?
Yeah,
But
but
you
then
can compute that from the distribution itself also.
possibly, I'm just.
I don't know.
That has to be considered once we do it.
See that this is not that's
So
an interesting PhD thesis. Yeah.
Okay, a naive question. So you do have symmetry between the projectile and target. Can you apply this symmetry to simplify your code? So I was thinking maybe you just like
Yeah, we are already doing that. We are at the moment only calculating one quadrant of the whole system, and by symmetry, exchange between the fluids, symmetry along the the z-axis and the y-axis, we only compute a quadrant of the system and copy it to the rest.
Okay.
Of course, if we do an asymmetric collision, we cannot do that anymore. So, first preliminary results. I'm very happy to show conservation first. So what you see here is energy and baryon number. Forget the baryon number, it basically is the same plot as energy. What you see here is in red and in green and yellow. Those two lines, they're exactly overlapping with each other. Those are that's the energy in the projectile and the target. So those lines here. Then we have the energy in the fireball, that's the magenta line. Here you already see the friction at work. So for a couple of Fermi, nothing happens. The two nuclei need to overlap for some time. I should mention this is at 3 GeV set of mass energy. Then the friction starts acting, and you bring energy and momentum into the fireball. So the fireball is building up, the projectile and
Touch it again.
touch which one?
I don't know. Maybe
No, I see you computer.
I think it's computer. It's not.
Oh yeah, the computer went to sleep.
Maybe you will kick out from Zoom.
I'll try to share again. Whole presentation went away.
Good.
No?
You drop off Zoom? No, you're still there.
I'm still in the Zoom. Let me maybe try to get off the Zoom for a second.
Strange. Did your PowerPoint or Keynote crash or what?
I'm using Keynote. So, back to business, Keynote. Okay, cool. Yeah, again, so short reminder. Oh, we moved
Touch
Push
it.
it with your fingers. Yeah, push it.
Or like you're zooming out.
Like squeeze it in. Something.
Okay, cool. Thank you. So again, short reminder, green and yellow, projectile and target. Magenta is the fireball that is built up while projectile and target lose energy and momentum. However, they don't lose actually all the momentum until the end, because this is a B=2 collision, so you have some spectators just propagating through without getting into the fireball. Then we have the sum of green, yellow, and magenta, which is all of the fluid, that's the black line. So we have the fluid, which is then turning into the part that is freezing out, which is the blue line. And then the sum over everything is the red line, which you see here. And we have a energy, momentum, and charge conservation at this energy of 0.01% relative loss of energy. The part here at the end that is actually larger than 0.01, but this is simply because at 40 Fermi we just stop, because otherwise it would take too long for debugging purposes. If we let that run longer, this will actually slowly tend towards the final value, or the total value. And what we are technically doing here is just enforcing, okay, everything that is left on the grid just freeze out. Okay. That's what we're doing at the final time step. And the 0.01 that is actually being lost without that final part is happening here, where you see that small kink in the function. This is where the first cells reach the edge of the grid. And when that happens, we double the size of the grid and actually also double the size of each cell. And when we do that, we lose a part of the energy. But compared to conventional hydrodynamics, 0.01% energy loss is actually quite good.
So you double the grid. Is it in the z direction or in the transverse direction?
What happens here?
Right.
That is a good question, actually. I never checked, but I would assume that it's in z direction.
Expansion is larger than z direction.
Yeah, because we put in the ensemble average initial state, the Wood-Saxon distribution. That tail of the distribution is already far at the future. That's up in the future, but that large positive z, strongly suppressed, but it exists. And I think the criterion for this is when 10 to the negative 8 or something of the whole energy is reaching the edge of the grid, we double the grid. And this, I think, is a tail of the Wood-Saxon distribution. Yeah, again, for a full physics simulation, we would anyways from the beginning on double the grid. At the moment, we are still debugging and everything. But even with that kink, energy conservation is quite good.
Also, when you calculate this total energy, what does it mean? I mean, is it local density, you sum it up, or you?
That's the energy in the computational frame. So in the center of mass of the system.
Okay.
So this is contracted by the gamma factor.
Okay.
The cool thing about the model is the continuous freeze out, where the hypersurface of freeze out is actually intrinsically done by the scattering rate and not from external given in by a given parameter. So what you see here on the left-hand side, this is a collision at 2 GeV. This is the energy in units of ground state, energy density at 4 Fermi over C, 10, 16, and 20. What you see here is initially the two nuclei are overlapping. So here you see the slow buildup of the fireball. Only in the center of the system, the temperature is, or the energy density is rising. Then you reach full overlap, and most of the system is now in the fireball. At later times, the fireball is expanding, and you see a part of the spectator that did actually not move into the fireball. This is seen here at the side of the system. And in the end, everything expands, and the densities drop again. Now, on the right-hand side, at the same times, you see the energy that is freezing out at this time. So very early on, nothing freezes out. At 10 Fermi over C, at full overlap, freeze out can only happen from the edge of the fireball, if you map that onto here, because in the center of the system, although the emissivity is very large, the probability of escape is approximately 0, because you have to propagate through the medium. At even later times, 16 Fermi over C, that's my favorite picture actually, because here you see in the center of the fireball, again, nothing is decoupling, because although, again, emissivity is large, the probability of escape is very small. However, at the edge of the fireball, you really get a ring which has the perfect combination of rather large emissivity, but also in the future, the system is becoming less dense, so that the probability of escape has a significant value. That's what you see here. And this is, as I said, really determined by the local interaction rates and not just put in by hand. And in the end, also the center of the system is decoupling, because at the end has to.
So the spectators don't freeze out, right? I mean,
at the moment, the spectators don't freeze out. We can also do that in the future. We just have to plug in for the Gauss-Laguerre thermal distribution for the nucleus,
sure.
but at the moment that's not being done.
Vertical axis, z-axis.
That is Z and X. So the nuclei are moving like this. Thermodynamics in the central cell. So in the central cell of 5 times 5 Fermi, that's the evolution of temperature, the chemical potentials, baryon, strangeness, isospin, the pressure, and the expansion scalar. And one thing I have to point out is, because as mentioned in the beginning, we don't have a continuous transport of baryon number into the fireball yet. We do this unification, which has to be quite large to have μb in the system. And this leads to this somewhat artificial early increase in temperature and the potentials, because until this time, there's no baryon number yet. That's why there's this early weird kink. Later on, you see the typical behavior. So the temperature increases, it slowly fades out. The chemical potential increases and more or less stays constant. Pressure increases and fades out. And in the expansion scalar, this is only calculated for the third fluid and not everything. You see there's a compression phase until whatever 10 Fermi over C, corresponding to the time of full overlap. After then, you turn into expansion, where you see the typical Hubble-like behavior. And in general, the blue line is the pure hydrodynamic simulation, and the red line is the hydrodynamics plus continuous freeze-out.
So why is the chemical potential constant after a while? Shouldn't that go down? I mean, the density goes down, right? Why is it expanded?
Because it's grand canonical and we conserve baryon number. So once the system starts to decouple, μb always has to readjust to still keep the baryon number in the system.
Okay. All right. I have to think about that. Yes.
That's the time evolution of the nucleons and the pions. Let me just focus on the nucleons first. What you see here is, in red, nucleons in the fireball and the projectile and target. So it obviously starts at 400 or 394. Then it decreases because nucleons go into the fireball. And in the fireball, nucleons go into resonances. That's why this increases. If I would add up the resonances, this would be a stable line. Then at some point, the freeze-out starts to kick in. And here we have separated freeze-out into direct nucleons. So nucleons that are sampled as nucleons from the equation of state. And nucleons that come from the decay of resonances, mostly the delta, which we also do with the sample with the equation of state and let them decay. And that's the only Monte Carlo that we do in the simulation. Yeah. And then for the pions, you see the same. In red, you see the pions that are in the fireball. You see in magenta the pions that are directly emitted as pions, the pions that come from the delta decay. In both lines, then the blue is the sum over all of these. So that's the number of nucleons and pions presently in the system at each time. And one fascinating thing is the pion number that is finally measured, and here the yellow line is the preliminary star data. This is 3 times the number of pions that is maximally thermally in the system. And this is due to the continuous drain of energy and baryon number from the system via the continuous freeze-out procedure, which is, I think, quite fascinating.
Wait, I didn't get this. So the yellow line is what?
The yellow line is the star data.
No, the other orange, I mean. Orange.
This one?
Yes.
That's what's thermally in the fireball.
Thermally.
If you sum over the whole grid and just add up the thermal pion number in all of the cells, that's what you get.
So and then the blue line are total pions coming out at the end of the
That's thermal plus what has freezed out until that time. That is everything that is in the system.
That's the cumulative.
Yeah.
Oh, the star is, of course, some kind of an integral over that stuff, right? Okay, okay, got it, right. Thanks.
But the measurement has some kinematic range,
right? This is 4 pi extrapolated.
Oh.
So that's I fitted the Gaussian to the rapidity distribution and just integrated that, then you get roughly to that value. Yeah, actually, if you compare to the E800 whatever data at 2 and 4 GeV, that's much different. I don't know what's going on there with the data, but usually we fix everything to hit the 3 GeV data. As I said, we're still in the debugging phase. I can show you freeze-out distributions. So this is the NDT as it is, and then normalized to compare the different particle species. Basically, what I want to point out is that protons and pions, so red, blue, and magenta, have a long tail to later times because we freeze out the whole system, all of energy and baryon number. And to ensure that, well, pions and nucleons must freeze out until very late. On the other hand, all the strange particles decouple quite early. So this early peak is before we have baryon number in the system. But even here, you can see a slight separation between the strangeness and the light, the bulk of the matter. We can do the same for temperature, the ND temperature and normalized temperature distribution. Here again, we see because we want to freeze out all of the baryon number, the freeze out of the protons goes really to very low temperatures, although the average is roughly agreeing with what is being measured at hardest and star. The same is true for the pions. And interestingly, here in the pions, we also see the split in isospin, which at large temperatures, they are degenerate. And if you go to lower temperatures, they are split by our isospin procedure. Here you also see that the kaons favor decoupling at the very high energies, and at very low temperatures, they are suppressed.
So if I take this orange curve and
Right.
integrate it over the temperature, I get the protons. Right?
You get the protons.
So just chi by I, if I look at protons below 50 MeV temperature, that's about a third.
That's half to a third, yeah.
This is surprising.
That's quite a bunch. I can tell you, we have checked.
And the spectra come out right, more or less?
More or less. I will come to that. What we have seen is, because we are still adjusting parameters and changing some of the physics, these distributions can be quite different in different scenarios. This is what we at the moment find the most physical. But the general trend that it stretches down to 20 MeV or something, that is consistent across all the versions that we have tested. On the left,
these guys have floated. This is really the local temperature.
That's the local temperature.
It's not the spectrum.
No,
Okay.
no.
So that's
It's the local
float.
temperature.
Okay, yeah. Okay. All right, cool stuff.
But I mean, but for your QMD or whatever this afterburner model, they use like a 140, right?
So they use whatever comes out. They just do cascades or whatever, transport.
Yeah. In our chemical freeze-out study with UQMD, we also see a very broad distribution, not going down to 20, but going down to 50. Yeah, I think here one just has to admit we got primed by everything is super thermal and freezes out at one fixed temperature. And this is really so stuck in our minds. A separation in temperature in the end is somewhat physical. What I find interesting is on the left-hand side, you don't see it because that's not normalized. But the antiprotons, although not many, they freeze out at a very specific temperature. So they don't show a huge spread in temperature, which tells you the freeze-out contour for the antiprotons is very precise. They must meet very, very specific conditions to freeze out given the emissivity and the probability of escape. That's the same for chemical potentials. I will skip that for a moment. And now we can plot this into the phase diagram. Here only shown for the pions. You see the chemical freeze-out points as these dark blue stars in the back. I've put in the chemical and kinetic freeze-out from your QMD. This is the parameterization by PBM. And this is what we get at the center of mass energy of 3 GeV for the pion freeze-out. And first of all, you see that this is spread over a huge range, which also tells you that, for example, these fluctuation studies that they don't show a very precise peak at what energy, but are really spread out across many energies. But also you see that roughly averaging about it, you end up in the roughly correct region in comparison to the experimental data.
So what percentage is blue of the pions?
This one here?
Yeah, the blue area, if I integrate over this. You don't know? 50%. I don't know.
Yeah. So this is in temperature from whatever, 40 to 80.
Yes.
If we go back.
Okay, that's easy. 40 to 80.
Half.
Half, okay.
Roughly half.
All right, good guess.
So actually, in this plot, you have some cells at 0 omega V, right?
Yeah, that's the very early particles before chemical potential comes into the fireball. So there's a small fraction of pions that freezes out very early. Here also the system gets very hot because we don't have yet chemical potential. And that's again stressing we really have to find a way to put a baryon number in a consistent way and continuous way into the fireball. Then we will get rid of that. Excitation function and yields. So on the left you see for pi multiplicity, on the right mid rapidity yields. At the moment only shown for protons and ions. Although I have to admit the quantitative agreement is not super great going to higher energies. At the lowest energy, at least for the pi minus, we agree with the E800 whatever data. Star is not put in here, which we have adjusted our parameters to. And at mid rapidity, the situation is similar. Qualitatively, we get all the trends. Quantitatively, we are not yet where we want to be in the future. And also for the protons, the qualitative trend going towards these points seems to be established also for the antiprotons coming up here. For the protons, for example, at these low energies, also clusters need to be taken into account, which will decrease the protons and get closer to the data. When considering strangeness, everything is not so good as for the bulk of the matter. But again, here, qualitatively, for the kaons, we get the trend. For the lambdas, we get the trend. For the antikaons, we get the trend. Also at mid rapidity. But because we don't have global strangeness conservation and only local one, this cannot be taken serious yet at the moment. Rapidity distributions here only show one example at 3 GeV, admittedly, where we have fitted our parameters. But here you see that the protons and the measured protons agree quite well. This will come down once we include the clusters. For the pions, the agreement and the shape is quite good so far. For the kaons, so this is our calculation. The black ones are the kaons measured by star. As I said, we don't have conservation yet. And also at these energies, one typically needs some mechanism to suppress the strangeness, and this is work in progress. And finally, for the spectra, this for the first time showing something at 7.7 GeV. What you see here is pions in blue, protons in black. At mid rapidity, and the left-hand side is the ideal hadron gas. The right-hand side is where we have already plugged in the excluded volume with 0.3 Fermi for the excluded volume. And I think the major observation is that the excluded volume decreases the pion number. I mean, that's a log scale. You don't really see it. But if you zoom in, you see that the excluded volume suppresses the pion number. But I think the general feature here is that we get the slope of the distributions quite well, also having flow on the protons, which so far I think is quite good. And with that, let me summarize. I will just read that slide out. So Frisco3 is a novel 3-fluid model with dynamical generation of the fireball due to friction and unification, incorporating a continuous freeze-out mechanism based on the local scattering rate. It is applicable for heavy ion collisions in the range from 2 to 20 GeV in the center of mass, which is exactly the energy regime where fair and star fixed target will be operating. It overcomes many of the problems of conventional hydrodynamics, like you need a fixed initial time to produce your fireball, the simplified freeze-out, no feedback to the hydrodynamics. However, we still have a lot to consider to really make it fully physical. We have exact conservation of energy, momenta, and charges, at least baryon so far. The preliminary results look highly promising future for the model. And it is ideally suited to study phenomena in the fair, and as I said, star fixed target energy regimes like yield, spectra, flow, HBT, dileptons, in medium modifications, and so on and so forth. And with that, thank you for your attention.
Thank you. Thanks for this nice talk. Questions? Yeah, go ahead.
My voice is bright.
Will it be possible to describe the out-of-plane expansion and low beam energies?
We have checked that. At the moment, the out-of-plane is not really reproduced by our model. We think the problem is that the fireball is actually expanding through the spectator, because from a pure hydrodynamic point of view, the fireball is not feeling the spectator or the projectile in a target. And we are thinking of putting the total pressure for all of the fluids together instead of putting the pressure only for one fluid. We think that will fix the problem, but at the moment we don't describe it.
Shin?
Hey, Tom, very nice talk. I see, yeah, certainly the focus on the yield comparison. Do you have the comparison for the like mid-central collisions or
No.
curve? That's still, and what's a hope there or?
So far, I've only calculated once mid-central collisions for the previous question to check what flow does. For the yields, I haven't checked it, but I have the data on my computer. I can just plot it and show to you later.
So basically, you can do for the mid-central collisions, or
we can do it, yeah, sure.
Yeah, just regarding the flow, basically that's. But I believe that'll probably come next for your comparisons, right?
We cannot do ultra peripheral when you go into a regime of having just proton-proton, but up to whatever 30–40% centrality, we can do that.
Thank you.
Okay.
Would you expect things to change, and if instead of the Wolf section distribution, we used something else?
Sure, yeah.
Like, so you expect this to be sensitive to that in general, like more than your accuracy that you're stating?
More than the accuracy? Good question, but I think physics will change. So from my intuition with the model, well, first of all, we need full consistency throughout the whole model to get everything correct, or everything consistent at least. What we have seen is if we change something in the initial state, not really this initial state, but in the friction term, the final physics actually changes quite drastically. And given that experience, I would say it should also be quite sensitive to the initial state, especially when we put in fluctuations.
Okay.
So maybe I mean, so the fireball is quark-gluon plasma or not?
No, at the moment, pure hadron gas.
But it can be adjusted, right? You can put
Sure,
in
yeah.
the right equations.
Sure.
I mean, but then here's the question. So where do you get the stringiness?
So locally, in each cell of the grid, we have an equation of state with rho s equal to 0, locally.
Okay.
But because, for example, the kaons and the antikaons, they have different cross-sections, when we propagate them through the medium, the kaons will actually freeze out early. The antikaons will get stuck because they
Where
have
does the
loss.
kaon come from?
Locally from sampling the
From the temperature.
from the temperature.
From the temperature. I mean, but when you first these two nuclei passing each other, my understanding your fraction maybe that coming from fraction, because you don't have quark-gluon plasma, so I would where does strange quark come from?
Friction just puts energy into the fireball.
I mean, strange has coming from somewhere.
Well, you heat it up and then you get what you see as well.
Or you basically get the K plus K minus.
Exactly.
Yeah, K plus K minus. Okay, K on lambda.
K lambda.
K lambda. Ah, I see.
It's just thermal, right, in this case.
And the kaon freezes out. The kaon.
Maybe you have that parameter to determine that, and that parameter is too big. That's why you get too many strengths.
We have checked this. The strangeness really needs total conservation, and it also needs a mechanism to suppress the production at early energies.
How you suppress it? I mean, so that's why I say if there's a quark-gluon plasma, you can easily produce that. If there's SS bar coming from ground splitting, right? But I don't know.
At the moment, no quark-gluon plasma. This is just K plus K minus from the hadron gas.
Volker?
Hi, Tom. Thanks for the nice talk. Yeah, I just have a question, and maybe I didn't follow it. So when you say in the summary exact conservation of energy, momentum, and charges, are you referring to
Baryon.
Conservation in which sense? In the sense of canonical ensemble, or in the sense that your integral at initial time is the same as the integral at other times? What does the
energy integrated over the whole system is conserved throughout time.
Okay, so it means exact conservation of average energy, average momentum, and average charges, right? But for instance, if I would consider fluctuations, I would also have to consider conservation in the sense of canonical ensemble of conserved charges.
If I get your question right, if we would do a fluctuating initial state, we would also conserve energy and momenta. Just the distribution of energy is different in the system.
Yeah, but if I would be interested in a cumulant, for instance, would it provide just a Poisson distribution for baryon number?
Well, that's a good question.
But how would you do this, Volodya? I mean, then you would have to do multiple events and then get the cumulants. I mean, I mean,
but even let's say you have multiple events which for some reason have the same initial profile, you would still have this effect of conservation loss. I mean, I don't know how to do it. I just wonder what is exact conservation here means. And I understand that at the moment it means that the integrals of the average energy and other quantities are preserved by the simulation, right?
At the moment, the sum over the whole grid, where the grid and the part that has frozen out is conserved.
Exactly. Okay. Well, these are the first moments of energy, momentum.
These are the first moments,
Okay. And I think also you mentioned strangeness and canonical effect. So are you, does it mean the canonical suppression, which would modify the equation of state that you use, or is it something else?
Yeah, something like a canonical equation of state would help for the strangeness. However, also in that case, we need to extrapolate the equation of state along many other directions, actually for every particle species. And the precision that we need in the equation of state to conserve everything is so small that this is at the moment not feasible.
Oh, okay. Yeah, right. Because I guess that the equation of state, if you take hadron resonance gas and we consider the amount of strangeness that we have, let's say at 3 GeV, the corrections from canonical ensemble are significant to strangeness, right?
They are like 95% or something. If you talk in terms of gamma S, I think it's like
not gamma S, not gamma S, the canonical.
Yeah, not gamma S, but the gamma S usually is like 95 or something. So
it depends. It can be quite low for Hades, for example. Okay, I see. Okay. And if I may, I just had a comment on the first 3 slides where you showed the figure. And I appreciate the acknowledgement of our recent work. I just wanted to mention that the work has mostly been done, the heavy lifting, by Hitansh Shah, a graduate student in Houston. And I think the proper citation reads et al. That's just the only thing I wanted to mention here, but acknowledge that you put this recent prediction in compilation. Thanks a lot.
I'll modify. Thank you.
All right. No more questions? Then let's thank Tom again. And again.